Was हाँ जी ऑडियो ऑफ कर दो.
Minimize the question screen.
Okay.
Question screen is visible.
Okay. Should I start now?
I can't
Yeah.
see Shehzad.
Okay. Can't see. स्टार्ट किया ना. शो स्क्रीन तो क्या हुआ है? मेरा स्क्रीन है लेकिन मेरा वीडियो नहीं चालू है. अच्छा इनको नहीं.
किया
स्टार्ट कहाँ स्टार्ट करूँ?
स्टार्ट हो गया है सर.
Okay. Should I start now?
Yes.
Okay. Good evening, everyone. Welcome to this 11th edition of Tiscon eDiscovery. Now, first of all, as it is customary, I would like to thank all of you for coming up and turning up on this beautiful Friday evening, and also for Tiscon to have brought us all together for this wonderful opportunity. And I think now people can see me now, and feel free to drop in your questions into the question box now. Whenever you feel like through the presentation, we will be taking the questions at the end of the presentation. Now this presentation should last roughly around 45 to 50 minutes. I'll try to wrap it up as soon as possible. There is this handout that has been given to you, which shall cover roughly the contents of what we are presenting. There is also a survey, I feel, a feedback, which will be sent to you at the end. I would encourage you to fill in the feedback so that they can bring you more interesting content. And so let us, with no further delay, start off with our presentation. This presentation is roughly is not going to be very technical. Those of you who have some technical questions, do feel free to drop an email or put it into the question box. I'll try my best to answer them. For those people, I've kept it a bit more generic, and I hope you enjoy the presentation. So let me start by saying that generally when we look at structures, conventional building structures, we come across flexural systems, that is bending systems. So we have beams, we have deflections in the beams, and we will calculate the stress that is there in the beam, be it the bending, the shear, torsional stresses, and accordingly design the stiffness so that it doesn't go into a lot of deformation or deflections, and accordingly we design the structures. But there are a whole new different type of structural systems which respond to stresses by large displacement, and these are what we call as soft shells, and they change their geometry to fulfill the equilibrium equation. So to stabilize such geometry, we would have two opposing curvatures in perpendicular planes to so that they balance out the positive tension forces. So now we have what we by the flexural systems, we have systems which are surface structures, which are surfaces which are developable systems, which are flat, which have a Gaussian curvature of 0. Now, when we say Gaussian curvature 0, they are developable surfaces. So the thing is, you could make it out of a sheet metal or a very plain kind of paper or a fabric. But there are also this whole different set of geometry which are non-developable surfaces where the curvature is less than 0. Now, these surfaces are what we call as anti-clastic surfaces. Now, anti means opposite, clastic means curvature, so they have opposing curvatures. If you see over here, you will see a blue line which is going from the high point to high point, and the red line is going from low point to low point, and these both curvatures are opposite in direction. Now, so basically these cannot be developed so easily. they cannot be folded out so easily without sufficient amount of algorithms because they are geodesics. And then we have, so then the question really is that if you have 0 and if you have less than 1, then what surface do you have if the curvature is more than 1? So we have what is classically called the cushions, the shells, the paraboloids. So where you have both the curvatures are going along the same direction and are along the surfaces, and these are inflated cushion kind of surfaces. So when we talk about design and analysis now of tensile structures, now we need and when I talk about tensile structures, I purely talk about high tension structures. I do not talk about tents, or I do not talk about canopies, because those are very low tension, low pre-stress kind of structures. They need to have a certain amount of negative Gaussian curvature. When I'm talking about single layer curvatures, not talking about cushions. So they need to have a negative Gaussian curvature, so that the thing is the stress is log, and you have a uniformly stressed structure. Now, most of these tools that are based on 3 or 4 different types of algorithms, which is force density method, dynamic relaxation, non-linear FEM methods, natural force density method. These are all methods, algorithms, mathematical models to achieve our tensile structural systems. And it's now, let me just go through the systems to tell you about what those systems are about. Force density method has been around since 1970s. Now, it was the math that was written to design and analyze the cable nets of the Munich Olympic Stadium. It's very fast and it's very easy to understand. It's quite robust. It's been used worldwide, and it's able to solve a plethora of different types of geometry, and mainly non-uniform distribution of stress is also possible. But the disadvantage with these systems is that it's difficult to mix different mesh orientations, because you would require geometric alignment of mesh, quadratic alignments of the mesh. Now, shear stiffness is neglected, so in most cases is not so much of an issue. But when you find extremely asymmetrical kind of structures, there is like cones, there's high amount of stress concentration on the end points and on the head ring, and and there's also shearing that is happening within the membrane. So this is neglected, and this is not being able to be plotted in using force density method, and so it's difficult to use these kind of systems for such kind of application. No, it's very apt for using in systems where there are variable stress distribution, like conical shapes, like pagodas, and so on and so forth. When we talk about nonlinear force density methods, we have got this is the algorithm for finding out force in linear. I won't go into the math right now. Now, basically, it is for more kind of a linear oriented. So if you see, the thing is that this curvature, there is a curvature here, but then over this, in this axis, there's very less curvature, and hence it is force density method would be a right algorithm to use for this kind of forms. So you have what we see, the grid over here with stresses on them now, and as elements, and each of them as stresses. These are the kind of structures that you would design using force density method, because you would see the warp and the weft having different elements of stresses. When we talk about nonlinear natural force density methods, now URS and NFDM are good approaches, because what happens is that you work with your triangular meshes, and you work directly on the meshes. So you work with surfaces and not only a grid or a quadratic kind of an setup, and you are able to do a lot of continuum surfaces using NFDM. But in this method, the warp and the weft orientation has to be assigned, because without assigning you will not be able to track the shear stiffness. And that brings me to the weaknesses of this systems, is that they are very difficult to find and define non-uniform stress input. So if you're talking about cones, if you're talking about continuous cones and rectangular cones rather than squarish cones, it's very difficult to find the form using NFDM. Similarly, now it also because we need to get in the shear stiffness, we also need to the Poisson values, and the Poisson's values are not usually available or are not calculated by the fabricator, and it varies a lot depending upon the pre-stress we have and for each load cases. So it becomes slightly way more complicated rather than slightly than FDM to analyze. These methods are usually suited for cushions, for minimal surfaces, and membranes with uniform distribution of stress. So URS, this similarly again NFTM was developed by Roy Pagliatti, and URS was developed by Kaiue Bletzinger. And as I said, these are the kind of forms that you should result in. Uh, when we talk about another method, which is called the direct stiffness method, which is based on FEM triangular and quad elements, and in which again shear stiffness is taken into account. It's a much more technical form finding method, because you are inputting the membrane pre-stress as an input, and so it's actually like saying that we are pulling a certain membrane with certain pre-stress, and what will be a form. So we are directly inputting the stress and directly getting the form according to that. Now the advantages is that it's very good for structures like tents and tarps and inflated structures. But what happens when we are dealing with very complex forms, it's extremely difficult to converge these kind of matrices. And again, the Poisson's ratio is extremely critical, that it be accurate as possible, and which is not usually available. Now, a wide application is inflatables, now where we know roughly the form that we want. Already we know the form that we want, and we just want to get the overall pre-stress and the stress distribution over the surface. So to give you an example of a similar kind of thing, this is roughly the tent that we are looking at. It's an inflatable with cable and cable at four corners, and then you can see that it's not an uniformly distributed stress over the membrane. There is certain areas, which is certain very concentrated areas, where we have stress up to 5.6, while overall we have somewhere between 4 and 5 over here, and then again concentration somewhere over here. So this is S22 stresses again, and again you see there are certain stress concentrations over there. But we are okay with this, because the thing is, we know as builders that we will tend to reinforce this with double layer or triple layer, and we'll be able to get out these stresses. But overall we have the actual pre-stress that we are looking for such kind of a structure. So just to give you an example for this one, but so I'll just get out the answers. We would tend to do FDM for this kind of a structure, because we have it the grid quite quadratic, and we have got a variation of stress completely over the membrane. We would do an NFDM or a URS to get as close as a soap bubble film for these kind of structures. This would be an NFDM because we want as much of uniformly stressed surface as possible. And this obviously, when we are taking when we are taking a stiff piece of, let us say, 2 mm sheet of aluminium, and then assigning certain forces, and we want to see actually how that piece is going to deform, we are going to use the direct stiffness method. So what happens is usually that if you have a linear FDM or a non-linear FDM module or a URS module, the thing is that you will first find the form and you will get the pre-stressed membrane or the cable system. And then the thing is you would put your supporting structures, which will plug into your non-linear FEM module, which is the finite element mesh module, and you get your final model for ready for other processes and so on and so forth. So this is roughly the path that you would follow. The reason why I would separate the form finding module out is because the thing is there's a tendency to, if you're not very experienced, or if you don't know your final target pre-stress or your target form, you will go into a loop between the form finding and the pre-stress a lot before you achieve your final form. And if you do it with the supporting structure, it will tend to be a very long process. So the real idea would be that you finish your loop here, then you come in and do your analysis module, and you get the final model ready for other processes. But tensile structures, as we know, are not only for membranes. So what happens is that usually people will work with coupled or uncoupled analysis. So what happens is that they will do the form finding, get the stresses in the warp and the weft, and then put the structure in another software and get the forces there into the other software to design the steel. Now, I'm just giving you an example, a very quick example, that in this case, that was the uncoupled part, but this is the coupled part where the structure and the membrane is in the same software itself. So here you see the coupled analysis where you see a certain amount of deformation. It's around 140 mm. And again, if you'll see the node displacement, 145 mm or so. Now over here, the beam will tend to rotate and come in. And then you have, because it is coupled, you would have the stresses in this cables, which is around 191 kilonewton, and at the beam bottom, which is around 343 kilonewton. Now let's do an uncoupled analysis. So when we do the uncoupled analysis, obviously these nodes are fixed, so the deformation displacements, if you see, are much lesser, obviously, because this is not rotating and coming in and it's not losing pre-stress. But then when we take these forces and when we apply these forces into this system, and if you see this, now we will get our forces in our cables and in the steel elements. And here you see now the load is around 537. So what does it mean? It means that when we do a coupled analysis, now the deformation for an uncoupled reduces by almost 23% in this case. But when we talk about the forces increase by 30%, and the actual force on the beam, if you see the reaction beam axial force, it increases by 56%. And similarly, the reaction at the foundations, it increases by almost 30%. So which means that when we design in an uncoupled way for a pure tensile system, what happens is that we will tend to design our foundations with at least more 30%, up to 30% heavier. Similarly, the steel structure which is supporting our tensile structure would be much more, which will have around 56 to 60% more than what is actually happening in the structure. So it is very important that we design it in an coupled fashion rather than in an uncoupled way. So how do we go about doing this? So basically we have what is called as conceptual design, where a sketch from an architect or a designer goes in. We have the form finding, the structural analysis, the structural design, the patterning, connection details and installation. The design process usually starts with the architect making a sketch. The experience of the architect or the engineer is usually makes the decision between a good and a bad solution. A good concept at the beginning results in a smooth job because you converge your design faster, you don't have much changes. But a bad one will become a nightmare and is generally very expensive to build, or it might not even be buildable because they do not follow the stresses. So now usually you'll find an architect coming in with a sketch like this, saying that, and this relatively architect is quite clear about what he wants. So he says that, okay, I have got an incline member with tie down cables, now certain height difference, certain proportion requirements, and then you put it into the program. You do primary 3D modeling for them, certain day views, certain night views, so that the client, the customer can get a real feel about what he's expecting out of the structure. And the deal is done. This is the price. You go ahead and you start constructing the thing. Now, because it was built with such a lot of clarity, is when you can do this much amount of detailing, or you are clear about how the tensile system is going to work out, and it works out pretty well, because this is what the original sketch looked like. So how do we go about doing this? So basically what we do is that we involve the primary structural system now and make the geometry elsewhere. Then we have the cable truss system which goes in. Then we have the secondary supports. We put the whatever the membrane flaps or the cables that we want, and then we finally go about designing the foundations. So this is the initial mesh that we are looking for. Now we assign basically an uniform tension, which will give us the final length of the cable, and this we get the reaction forces over here, which is through this central mast. Now, so we fix a cable force of 5 kilonewton, and this length we are allowing it to change so that we have a uniform tension in the upper cable and in the lower cable. And basically what we do is that the upper cable will have lower tension, and the lower cable will have more tension, and that's why it will pull out and make this kind of a form. And similarly, after that we are done, we know, so we have done our initial form finding with our nodes fixed and to get the form, and then we will incorporate all the structural system with so we got the form find, and then we'll incorporate the into our final structural system to understand the direction of the principal stresses and the supporting stresses. And then we merge the model. So the ideal way is, as I explained, that you first do your form finding separately, you converge on the shape, the height, the ponding, the wind forces, have a rough idea of what your changes in the form and etc. is required, and then involve the non-linearity of your structural system. So this is the final structural system relaxed with final reaction forces, for which you shall be designing for the foundations. And everything, if you see, they are in axial forces. No, they are in internal bending moments that will be there, but the whole structure is in axial compression or tension. So now the model is ready for detailing patterns and analysis. And so you see the frames, the flexuals are pure stress systems, and you can hence you can always use the optimum size of the sections. So this again, the bending moments, if you see, these are the axial forces, and this is what you see is the deformation of the system along with the membrane and the central truss, which you see is extremely light, for a 115-meter cable truss. And this is to show you how we do the patterning, and this doubly curved curvature is then cut into strips of fabric which has offsets, and they are welded together to formally make the final membrane. And this is how the patterns look like. So I'll take you through a couple of case studies about how we go about designing the structures so that you can understand them better. This was a project that was done in Bogota, and clients were a very big builders, Sambil in Bogota and Venezuela. And basically the roof is shaped like cuatro. Cuatro is a four-string musical instrument, and that was the main idea. The total foundation area is 180,000 meters square, and it has over 2,500 parking spaces with 260 commercial premises, so and so and so forth. The roof itself is around 4,500 meters square. Again, being South America, which shares similar kind of cost issues like our country, now at the same time requiring a very European kind of finish design. The type of membrane that they wanted to use was pretty low. So basically, this is the whole structure, and this is the roof, this is the glass dome, and this is the mean span of the structure. So this is the cuatro, as I was talking to you about, which is a four-string instrument, and this is the initial concept of the client. So you see it's very flat, quite, and 4,500 meters square you will not be able to achieve with this kind of flatness, because there would be serious issues of water ponding and so on and so forth. Fortunately, we had the architect on our side, and this is what the final structure looks like. So how do we go about designing it? So basically, from the architect's model, this was what was developed with the mast, with a uniformly stressed cable grid and a glass roof and a floating glass dome over here. So this is the integrated model of the steel and the cable net. You see the cable net below in the blue lines, and the fabric as the black lines. And this is what is happening on site. So basically, you see the people working on there with this whole steel truss which is suspended from this cable net, and this is what it looks spectacularly from below. And the membrane is supported over the cable net, hence we could go with a lower grade of membrane in this case. To give you a brief about parametric design with Grasshopper, so many times because of this looping, we have got now recorded history kind of systems where we can keep on changing the parameters that go into our designs, which dictate our design, and create models and very quickly change the parameters again and come back. Those people who use Grasshopper or Dynamo would understand what I'm talking about. So this was a small project which actually originally just covered this area, but then the client wanted to cover a bigger area, so which you see is quite huge. And this was the initial concept. Now, obviously, it has a lot of flat area again, which would never work. And there were certain initial concepts with cable trusses and beams, and then this was roughly what was accepted as the final concept, buildable concept. So basically, Grasshopper and Ice Cube is able, you tend to get a lot of back and forth that you can do in the design in terms of shadow studies, in terms of the analysis of the beam sizes, and so on and so forth. Here is what you see, the model. And so this is the initial stress, now, which is relatively uniform if you see overall in this area. And this is the warp stress or the wave stress in the second direction. This is because you have a cable net over here. So basically, as I was talking about parametric design, many times it happens is that initially we have a concept, and then we push it through wind interaction or through a CFD model or a computational fluid dynamic model, and we result with a huge amount of stresses at stress concentrations, and then we have to go back or either over design our elements to take the stresses. In this particular case, it was very fluid because the thing is we could take it into the CFD model, take the stresses out. So we had different directions. So here you see a lot of stress build up with CP's values as high as zero point 0.7 over here and negative values going up as -2, which obviously is not possible when we talk about codes, because most of even international codes, British codes and European codes, do not have sufficient amount of wind tunnel data to support these kind of structural systems. And it's very difficult to make out these kind of CP values without doing an wind tunnel test. The usual approach is to do a uniform wind pressure or wind suction, but as you know, we are just handling the static behavior of wind, and that's a very small aspect of wind. A greater aspect of much greater aspect of the wind is in the nonlinear, non-static kind of response of wind. So here we have the wind pressure loads, the CP values, right from, as I explained, from the CFD. And this is again in a 180 degrees direction. And then the thing is that based on that, you can design or redesign these structural systems. And as you can see, you can tend to result in 31 different load cases. But using parametric design, you can still keep on changing your initial concept and parameters and keep on developing a better and a better structural system. Here again, a little bit of explanation on the membrane stresses. Now, this is a type 2 membrane, I think. So this is warp versus weft is 32 kilonewton and 24, and the factor of safeties are roughly higher than what is expected, and hence we are able to get this. This is showing the steel process post processor in the software itself, and this is showing the profile list. So that, if you saw, was the factors of safety. So as expected, now none of them are going. So they are about, I think, 0.4, and this is blue, which is more greater than 1.64. And as expected, they would have the maximum bending moments here. And then these are the member sizes. Another project, about 1,000 square meters. Initial concept were very rudimentary. This is what the site was given to us. This is the kind of details that comes. And so we designed a complete roof system where you had this is the initial warp and the weft and the displacements. This is the envelope shear results, and this envelope moments. So it was designed as a space frame instead of Miro system was thought of because the client was extremely short on time. At that time, the design period was just 15 days, and they expected wonders, but it's still not built as yet. So this is what happens. Anyways, another concept, another similar location, 60 meters by 60 meters. This is what was expected. No supports at center. Again, similar kind of details. And this is the final structure. So as compared to the original concept, we were able to pull down the steel considerably in this particular case when you see the warp and the weft stresses in this. And so initially there were trusses all over, and here you just have the trusses on these main elements, which are itself three-dimensional truss systems. It does not end there. Basically, now we are looking at developing parametric end plate detailing and steel structure detailing now of the whole structures, be it for head rings or be it for end plates, which all would be dependent on the project. So thank you very much, and I look forward to having your questions. Now, I think let's stop this. Okay. Right. So do we have questions? Yes. So the questions I have concerned, I have not ever seen a typical structure. Please give info from basics. I think I've answered this question. I don't know if I'm not answered. Please inbox me about the thing. Which software do I use? The software is called IXCube. I am answering that to you right now. IXCube 4-10. If you want any further information about the software, you can get in touch with me about the same. Will I get my query answered? Yes, you will get your query answered. I'm from third semester. Glad to know you. What are different types of fabrics available in India and who are the suppliers? So there is Search Ferrari, who is the pioneers for the fabrics in India. Then there is Maggie's, Mailer Technologies, which also is in India. Technologies, let me just type these down. There is Sattler, which is an Austrian company which makes the fabric, which are based out of Bombay. There is Sion, which is a Dutch company, which is one of the biggest makers of PVC coated polyester fabrics. There is also Vazaidag, which is a fabric manufacturer. I don't know their presence if they are still there in India. Hiraoka, which is a Japanese fabric, which also has a presence in India. They are all available. You can just Google them or get in touch with me, and I can answer you about them. Okay, so that was how do you apply horizontal loads? Um so basically, I don't know if you're talking about horizontal loads in terms of earthquake loads or if you're talking in terms of wind loads, because if you're talking about wind loads, as I explained, we would tend to uh, apply it perpendicular to the direction of the mesh. And when we talk about earthquake loads, usually these structures have very less mass. So what really happens is that when we are analyzing for earthquakes, the mass excitation is very less, and as a result we do not have on top of that the membranes undergo they are quite flexible systems, so they can undergo a large amount of deformations. I mean, in wind, to give an example, a 1,000 square meter structure would deflect up to probably a meter and come back to its original position. uh, so earthquake forces are not so critical when we talk about tensile structures. They can of course be analyzed and proved in the software, and just like you would use any other software to prove for horizontal forces. Um, is this software free to download for research and education? You can get in touch with me. I can send you a link for the software. The software is IXCube 4-10. It is taught in universities at the IMS Institute in Dessau, and it is given as free copies for all the members of that program. Now, I can send you a copy if you are looking for that. Okay, approx costing of your explained project. Uh, there are a lot of questions now. Okay. Um, Are there any kind of structure types? Of course, they are constructed in India. Now, you can go to our website now and see all our projects that we have done. We are also into a lot of design engineering of the projects, so you can get in touch with us. Now, airports, stadiums are being done. The Bombay Airport, Delhi Airport, uh, Goa Airport, Goa Stadium, Ranchi, even metro rail stations are done in Tensiles nowadays. Today's webinar is typical. Can we download the session? Yes, I think so. You'll be able to download the session. How to ask questions to sir? I think so. You're doing that right now. Please send your email. My email is right there. I can send it once again. isb@sbdw.in. I think so. This should reach all of you. Okay. What national codes do you use for calculation? IS 873 obviously for the wind and the load calculation, 800 for steel, IS 456 for concrete. It's the same for all kinds of structures. This is the next. I have given examples of projects in India, how to develop design in taking tensile structures. Uh, how to develop designs. As I said, you can go opt for a very tactical approach in the sense that you could use soap bubbles and you could use even stockings to develop your model in a very low cost manner. And then once you have developed your model, obviously it is best that you deal with a specialist in this field, because as I said, if the initial concept is not solid, you might result in a very expensive or a non-buildable structure, or have structural issues during the life of the structure. How to change the design to tensile structures? Tensile structure, as I said, is a completely different method of designing itself. You are designing purely in tensile, so it is opposed to the flexural system of designing structures. Approx costing of your explained project. A couple of projects were not built, so I do not know the approx costing, but in Indian terms, they could range from 500 to 700 rupees a square feet. When shear force and bending moments come, then how is it tensile structure? The shear force and the bending moments are in the supporting steel and not in the membrane. How do you apply blind loads? What about lighting? Just like conventional structures, you can do lightings. How does membrane in compressive stresses? Membrane are not so if you would have compressive, you would have tensile buckling of the membrane. If you have that, and you would have creases on the membrane if they are subjected to compressive forces. Can we for thirst? What's the limit of deflection that we need to maintain? Interesting question. There is no international standard on this for deflection limit, because these are pure stresses. So as long as it is structurally stable, there is no kind of a deformation limit, and these loads are temporary in nature. So as long as your structure is able to take that without fatigue and without deforming to an extent that it permanently elongates, there's no problem. No, even through design. Yes, of course, there are lots of failures that have happened in India for these kind of structures now, but there are too many to enumerate right now. How green are tensile structures? Tensile structures are very green because they use very less resources. They because they are designed so detailed, and the fabric is recyclable. So the PVC and the polyester can be separated out and used again into different products. Is any unit based Okay, final element method or any other method. No, you would not tend to use any other method except FEM for designing these structures because they are a continuum. Uh, Yeah, how do you minimize the load? Increase the size of the headring. That would be any references book, lots of them. Short uh, Daniel Shock is a good reference to start from. Email ID. Okay. Why are these structures not used in India? That's a good question. Mainly because of the costs. Secondly, is about the quality. They don't get. They tend to be compared with low quality products like GI roofing, where the welding is done on site. The people come on site and weld it, fabricate it, install it in a very shabby way. They paint it on site. There's no kind of a corrosion treatment plan. So they are compared to a lot of this kind of extremely temporary kind of works, which is unfair. And that is the reason why most of these tensile structures are not used. Another thing is that we have a very big fear about vandalism. So the thing is the fabrics tend to be very soft, and you would tend to you anybody could rip open a fabric with a cutter and could destroy the fabric. Thirdly, now people are afraid about fires. Now, to tell you, these fabrics are now fire rated. Most of these fabrics are extremely good. Now, what happens is that the fabric would tend to curl back, and the flame would just so it would not burn the whole fabric. It will not start spreading like wildfire. So it is actually very good to have fabric structures if you are planning for fire. Again, they will not form droplets and drip on the people below. So the people below who are sitting there are absolutely safe when it comes to fire retardancy. Uh, okay, what is the limit? Hmm. Develop the arch vault by such absolutely. The thing is that just as tensile systems are an inversion of compressive systems, so compressive systems are an inversion of tensile systems. So if you can develop tensiles, obviously you can develop compressive shells also. Any workshop to organize for this? Yes, there are workshops. There are places where workshops are conducted. There's a course. There's a master's course in IMS in Dessau in Germany. If any of you would like to attend, you can look it up online. What is the future of tensile structures in India? Awesome. I would say quite bright. Now, every year we are adding newer capacities, more amount of fabric manufacturers are coming to India. At any point of time, any member can go into, obviously the steel members will definitely go into compression. And that is exactly what we have to design for. The membrane obviously is always in tension. How is the ventilation done in such projects? Depends upon the kind of structure. If you have a conical kind of a structure, the by natural draft, the hot air would tend to move towards the cone head, and you would be able to easily drain it out using a vent, or even louvers. How much results differ if you use abacus? Actually, results should not differ if you use different softwares, because but then the thing is that Abacus would not have a form finding algorithm. You tend to use direct stiffness method, and that to punch in that right value, it is like a 1 in a million. And again, there are millions of elements in that structural system, so you'll have to assign such a lot of values, which is why it would not make sense using an FEA type of software. Why is it concave and not convex? As I explained at the beginning of the presentation, the curvature has to be a negative curvature. So anticlastic shape, if you want a single layered membrane, if you have a inflated structure, then it would be both sides, it would be air supported, and then you would be able to get a synclastic curvature. How Deflection steel members supporting the fabric will yes, steel members need to be designed according to whatever IS code or British code or Euro code you are designing according to. So they have to be designed for those deformations. Now, can we model this membrane as a thin plate in SAP? How would you get the form? That is the first question. And how would you get the stress which is resulting to achieve that kind of a form? Now, if you get the form in a software and again assign those mesh in the mesh in SAP, you would be able to get it, but it's quite a laborious and a long and a tedious process. Are this type of structures safe from fire? I explained that. What is the life of the structures? If you're using a PVC coated polyester fabric, warranties are 15 years. If you're using a PTFE fabric, they would be in excess of almost 80 years. Rainwater harvesting, yes, I have done Google, and there are many tensors like Easy and Indian. Can you share something about them? They are also good softwares. Easy and Indian are definitely credible softwares. What kind of corrosion treatment? Sandblasting and 2 coats of epoxy paint. Do you have any manual method of analysis? Yes, there are manual methods, but I will not be able to share at such a short notice. Types of steels used in these structures. Steels would be regular steels, cables, regular off-the-shelf cables. Structure life of tensile structure, as I said, 30 to 35 years. As I said, 30 to 35 years is quite a long life. I think, what about using tensile regions? Obviously, they have done a lot of tensile structures using snow loads. I could show you pictures of them with loaded with snow. Who will finalize the form, the architect or the engineer or the executing person? I think I'm going to stop taking questions now. Feel free to get in touch with me. The email addresses are on the webinar link, as also the presentation. Our website is on that. Do get in touch with us. I'd love to hear from you, and do respond to the survey at the end of the seminar. Thanks a lot for watching, and have a good weekend. Okay, done.
He didn't need to come inside.
Yeah, it's done, I think so.